Welcome on board. It is my pleasure to see you taking this course. We will start with a short introduction of what is mechanics. I will do that using a PowerPoint presentation, while later on the remaining of the course will be conducted using Lightboard, which is much more interactive and conducive to learning. We are surrounded by structures and objects. Some are still stationary, some are in motion, where each of them can be considered as the subject of study of mechanics. Mechanics is the science which studies forces and their effects. Such effects can be reactions, internal forces, stresses and strains, or deformations, displacements, velocities, or accelerations. The part of mechanics which deals with structures or objects which are in motion is referred to as dynamics, while statics deals with structures or objects which are in equilibrium. The object under study could be either a mass particle. This is the case where the dimensions of the object is small relative to the dimension of the problem. For example, when we consider the orbit of Earth about the Sun, where the dimension of the Earth and the Sun is small relative to the distance between these two objects, these two planets. It could be considered as a rigid body or assembly of rigid bodies in the case where the objects are very stiff and deformations can be neglected. It could be a deformable body, or it could be a fluid, in which case we talk about fluid mechanics. Classical mechanics is governed by Newton's laws. Newton's laws are valid only when we consider what we call an inertial frame of reference. That means when we study the object from a reference system such that when on a particle there are no resultant force acting, that particle remains either stationary or moves with a constant velocity on a straight line. Different inertial frames of reference move relative to each other with a constant translational velocity. Newtonian mechanics has certain limitations. First limitation is it does not apply when the speeds, the velocities involved, approach the speed of light. In that case, the theory of relativity applies. Or when the scale of the problem is on the atomic scale, in which case quantum mechanics applies. Newton's first law states the fact that if on a particle the resultant force acting is zero, that particle will either be stationary or it will be moving on a straight line with a constant velocity. This law is a direct consequence of the assumption that we are using an inertial frame of reference. Newton's second law states that the resultant force acting on a particle is equal to the rate of change of its linear momentum. In case where the mass is constant, this reduces to the force acting on the body being equal to its mass times the acceleration. Newton's third law is the action-reaction law, which states that if one body exerts a force on a second body, then that second body exerts a force on the first body, which is equal in magnitude but opposite in direction. Note that these forces are acting on different bodies and therefore cannot be cancelled out. Forces can be classified into contact forces and non-contact forces. Whenever we have two objects which are in contact, then each body exerts on the other body a force, action-reaction forces. Non-contact forces are electromagnetic forces and gravitational forces. Whenever we have two masses at a distance of r, these two masses exert a force on each other, which is again an action-reaction force, which can be shown to be proportional to the product of the two masses and inversely proportional to the square of their distance. Whenever one of these masses is the Earth, then we refer to this gravitational force exerted on the second body, which presumably is lying on the surface of the Earth, as the weight of the object, and rewriting the expression for the gravitational force, we can see that the weight of the body, the gravitational force, W, is equal to the mass of the body times what we call the gravitational acceleration g, which takes a nominal value of 9.81 meters per second square. Fundamental physical quantities mechanics are a set of basic quantities based on which any other quantity in mechanics can be defined. This basic fundamental set of quantities are length, which measures the distance between 2 points, time, which measures the time interval between 2 events. It could be positive or negative if the second event precedes the first one, and mass, which measures the inertia of a body to changes of its translational motion. Alternatively to mass, we can define as a fundamental quantity the force, which is the action required to change the translational motion of a body. Mass and force are related through Newton's second law. Let us look at some derived physical quantities. Area is length square. Velocity, which is distance over time, is length over time. Acceleration, which is the rate of change of velocity, is velocity over time. That means length over time square. Force, which using Newton's second law is mass times acceleration. So it is mass times length over time square. Pressure, which is force per unit area, which is shown here. And finally, angle, measured in radians, which is a dimensionless quantity, since the angle is measured as the arc divided, which is length, divided by the radius, which is also length. Now, to define any quantity, to measure any quantity, to define the magnitude of any quantity in mechanics, we need to have some units. Let us introduce the units for the fundamental quantities in 2 different systems. The first system is what we call the International System of Units, which uses for length the unit of meter, for time the unit of second, and for mass the unit of kilogram. Force is a derived quantity for this system, and it is called Newton, which is the force required. 1 Newton is the force required to cause an acceleration of 1 meter per second square on a mass of 1 kilogram. So it is equal to 1 kilogram times 1 meter per second square. Depending on the scale of the problem that we are dealing with, we might use units which are larger or smaller than the units we just introduced. And in the international system, for that, we use a decimal system approach, where the subunits are multiple of tens. For example, we use the prefix centi to define something which is 10 to the minus 2. For example, centimeter, it means 100th of a meter. Or kilo, 10 to the third, 1000. Kilobyte or gigabyte, 10 to the ninth. The second system of units is the US customary system of units, where the units for the fundamental quantities are for the length 1 foot, for time 1 second, and the third fundamental quantity in the US customary system is the force, physical quantity of force, with a unit of 1 pound. Mass is a derived physical quantity in the system, which follows from Newton's second law, and it is referred to as slag. The subunits in the US customary system do not follow the decimal system and are shown here. It is important to relate the 2 systems, and while time is the same, seconds in both cases, we need to relate, for example, lengths and forces. The length, we can see, is the relationship is that 1 inch is 2.54 centimeters, and in the case of force, 1 pound is equal to 4.448 Newton. In our answers, in our problem solving of problems of mechanics, it is important to keep an accuracy which is consistent with our engineering aspirations. In engineering problems, we want to present an answer usually using 3 or 4 significant digits. A significant digit is the first non-zero digit we encounter in the result. So in this example, the first significant digit is the number 1, and therefore we present the answer using only the first 3 digits appearing after 1, 139. Now let us see how we convert from one set of units to another set of units. This set of units could be within the same or within different system of units. For example, we could try to convert a velocity expressed in kilometers per hour to, let's say, centimeters per second. Now, as a first example, let us see how we convert the unit of mass in the US system, which is slag, equal to 1 pound per foot per second square, to kilograms, which is equal to 1 Newton per meter per second square. Now, to do that, we first try to establish the relationship between the units appearing in the two expressions, which correspond to the same fundamental quantity. The unit of pound for force, which appears in the first quantity, is related to Newton, which appears in the second expression, through the relationship that 1 pound is 4.448 Newton. At the same time, we need to relate feet, which appears on the left expression, to meters. We do not have yet this relationship, but we know that 1 foot is equal to 12 inches, 1 inch is 2.54 centimeter, and 1 centimeter or 100 centimeter is equal to 1 meter. Now, we are going to use these expressions to transform the expression of units from the first to the second. We do that by performing a series of multiplications with factors which are equal to 1 and therefore do not alter the result. And the objective each time is to eliminate units that we do not want to see in the final expression. So let's see how we do that. We first try to eliminate pounds. So what we are going to do, we are going to multiply with a factor where the pound will appear in the denominator, and on the numerator we appear the equivalent to 1 pound, which is 4.448 Newton. So this ratio is equal to 1, and therefore we did not alter the result. However, what we achieved is that now the pounds can be eliminated and we have already Newton. In the next step, we eliminate feet by multiplying with 1 foot over 12 inches, this factor, which is equal to 1, and which allows us to eliminate the unit of feet. Similarly, in the next step, we multiply with 1 inch per 2.54 centimeter, which allows us to eliminate the inches. In the last step, we multiply with 100 centimeters per meter, which allows us to eliminate the unit of centimeter. And therefore, the final expression involves only the units of Newton over meter per second square, which is the unit of Newton. So truncating and keeping only 4 significant digits to obtain a reasonable from an engineering point of view accuracy, we can establish that 1 slag is equal to 14.59 kilograms. This completes our short PowerPoint introduction of mechanics. We next will move to the study of vectors, and I'm going to do that using Lightboard.